Welcome to our second lectures on series compensator. We have already discussed an impedance type series compensator and the converter based series compensator. Now, we shall see that what are the features of the series compensation we have touched upon in a previous lecture, and we shall continue from that point onward. So, we know that actually we have discussed it. It is possible to have enhanced voltage stability by the shunt compensation. We shall see that how it can be achieved. Thereafter, improvement of the transient stability, same who has been discussed in case of the our shunt compensation, same will be actually designed here, and we will see that what are the difference between these two and where you will fit what. And power oscillation damping, these are the most desirable feature that can be enhanced or mitigate by the series compensation. So, let us consider that you have a variable impedance inserted, and what about the voltage stability. So, series capacitive compensation can be used to reduce the series reactive impedance to minimize the receiving end and the sending end variation. Since this impedance value is decreased, so Vs become close to Vr, that is a basic principle, and thus what happen, it prevents the possibility of the voltage collapse. A simple radial system with feeder line reactant X, series compensating reactance X and the load impedance ZR is been considered. So, see that what happen with the different values of X. So, this is basically the power in X axis and the voltage transmitted in the Y axis. So, it is just you have familiar with actually this graph delta versus P graph. So, and you have also the V graph. So, ultimately you can change the value of the voltage and for the some values of the delta. So, what happened, we can see that this is the uncompensated one. So, ultimately you can transmit the power, and thereafter if you increase the value of the X, so it will be double, and if you increase the values of X of actually 0.5, so it will be double, and if it is makes 0.75, it will be 3/4. So, thus power handling capability of this line increases. Similarly, but what happened, you can see one thing here, the value of the voltage does not increases. So, receiving end voltage will remain same, but the power handling capability will increase. This is one of the biggest advantage of it. We have discussed about the compensation of the leading and the lagging in shunt compensation. You can see that straight away power is been increased without and within a rating of the voltage. The nose point at each plot given for the specific compensation level represents the corresponding voltage instability. So, this is something we require to discuss. So, both the shunt and the series compensation can effectively increase the voltage stability anyway. Now, let us see the next. So, what is the comparison of the series compensation and the shunt compensation? Shunt compensation does it by supplying the reactive load demand and regulating the terminal voltage. So, it will play with the reactive power and the receiving end voltage or with the voltage regulation, and thus it will control the flow of power. Series capacitor compensation does it by cancelling the portion of the line impedance and thereby effectively providing the steep voltage source to the load, because you assume that Vs is steep, you have a steep gate and the value of the inductance will be reducing. So, Vs will be actually more firmly will be connected to the receiving end voltage. For increasing the voltage stability limit, the overhead transmission series compensation must have compensation is much more effective than the shunt compensation for same power rating or the MVA rating. We have seen the plot for the series and the shunt both. So, shunt will actually, since it is basically controlling the power by the VR. So, for this reason we will find that actually stator by denominator, if you are basically dealing with the denominator. So, V1 V2 by x. So, reducing the x by 50%, you straight away jump the power handling capability by 50%. So, thus shunt compensation is a great advantage, and also it ensures stability because it reduces the impedance between the sending end voltage and receiving end voltage, and thus it is very closely coupled with the more steeply coupled with the receiving end voltage. Now, let us talk about the transient stability. So, powerful capability of this the powerful capability of the series line compensation to control the transmitted power can be utilized for much effectively to increase the transient capability. If there is a sudden load change, then the transitions comes into the system, then accordingly you can actually change the power handling capability of the line dynamically. That we will see when we will discuss about the devices that actually do the job. So, then what will happen? Then ultimately we will mitigate the oscillation to increase the transient stability limit to provide the power oscillation damping. Let us take a case. Suppose that the system without the series capacitive compensation transmit the real power Pm, and let us also assume that both the uncompensated and the series compensated system are subjected to the same fault for the same period of time. Okay. Prior to the fault, both of them transmit power Pm at an angle delta 1 and delta S1 respectively. During the fault, the transmitted electric power becomes 0, while the mechanical input power to generate the and the mechanical input power generated remains constant. This is our assumption. So, what will happen then? Same we shall analyze with the two machine theory with a equal area criteria. Therefore, the sending end generator accelerated from the steady state angle delta 1 to the delta S1 and to delta 2 to delta S2 respectively, and when the fault gets cleared by the breakers. That this one is our accelerating area and this is a decelerating area, same has been discussed in the shunt compensation. This is without the series compensation. Thus, we require to compensate the critical angle delta critical, and value of the delta critical would be actually pi minus delta 1. So, you have to compensate within that limit. So, but what happened in case of this series compensation? So, ultimately what happened, this was your accelerating area, and since the power can be increased depending on this actually the impedance value, you can change the impedance value, and let us assume that this value is k equal to 1 by 3, and thus the transmitted power handling capability increases to the 50%, so 1.5 per unit. So, for this reason you can see that huge area is available for the deceleration, and thus huge gaps remains for critically clearing the faults. The accelerating energy is replaced by the area A1 and AS1, and after the fault clearing, the transmitted electric power exceeds the mechanical input power, and therefore, the sending end machine decelerates. So, we have to match these two area, and here is a huge area, huge margin is available for clearing the fault. So, the accumulated kinetic energy further increases until a balance between these two accelerating and the decelerating energy represented by the areas A1 and AS1 and A2 and AS2 respectively is reached with the maximum angular swing angle delta 3 and delta x3 respectively. And thus what happened? The areas between the P versus delta curve and the constant PM line over the interval is defined by this angle delta 3 and delta critical, and it is delta 3 and S delta critical respectively. So, you can see that huge margin here with the compensation. The margin of the transient stability represented by A margin without compensation, this one, and AS margin with compensation. So, this area is AS margin. So, we can see that it has enhanced the transient stability. Now, what we can conclude? So, this equal area criteria shows that a substantial increase in the transient stability margin. So, you can go back and see. So, this is the area and this is the time available. The increase in transient stability margin is proportional to the degree of series compensation. Why? Because if you can make it say 1.5 to 2, so this area can be more bigger, so this value will be shifted to the left hand. However, there is a practical issues because current will be so high. So, however, the practical capacity compensation does not usually exceed 75%. That is also, then if you compensate by 75%, so it will have a 4 time power handling capability. So, that is not less if you are dealing with the MVA level power, 1000 MVA power goes to the 4000 MVA. So, that is a huge amount of enhancement of the power handling capability. Anyway, so 75% for the number of reasons, including the load balancing with the parallel paths and the high fault current and possible difficulties to the power flow control. These are the limitation imposed by the power system people. So, we generally restricted our series control with the capacitive series control to the 75%. And of course, it is possible theoretically this increase become unlimited and approaches to the 100%. Now, let us see that how it will actually damp out the power oscillation. That is also a very important aspect of it. The controlled series compensation we have seen also in case of the shunt compensation, then let us see and compare with the series compensation. Control series compensation can be applied effectively to damp power oscillation. The power oscillation damping, it is necessary to vary the applied compensation so as to counteract the accelerating and the decelerating swing of the distributed system. So, cause of this power oscillation is overthrow or overthrow of a heavy load or insert of the heavy load in the power system or overthrow of the any generator due to loss of synchronization. So, what happened then? And then rotationally oscillating generator accelerates and angle delta increases, and thus electric power transmitted must be increased to compensate the extra mechanical power. So, you require to do the needful to increase the power handling capability of the line as supplied by the mechanical devices. Conversely, when actually power generation decreases in the line, so you have to also reduce the power handling capability of the line, otherwise it will lose the synchronism. When the generator decelerates and angle delta decreases, the electric power must be decreased to balance insufficient mechanical input power. So, these are the two conditions, and accordingly the impedance of the line required to be changed to accommodate the change of the mechanical input. So, the required variation with the degree of the series compensation with underdamped oscillation system shown with the undamped and the damped oscillation with an angle delta around the steady state value of delta 0. So, this is the undamped without any compensation. So, it will continue to oscillate. This is called hunting in a machine problem, and we have to damp out the oscillation. There is a damper winding of course is there in the alternator, but fax can also do the damping by switching. So, what happen, we shall so we can gradually damp out the oscillation. So, we can do that. That is something we will be discussing when we will talk about the devices, series compensation devices. So, this is the undamped one and this is the damped one. So, gradually it will reach the steady state value of the delta 0, where actually it required to be settled, and this is the power swing, and that also will settle with the damping, and where k is the degree of the capacitive compensation, gradually it will change, increase or decrease to accommodate the change of the mechanical power. The corresponding undamped and the damped oscillation of the electric power P around the steady state value is P0. Okay. So, the third waveform shows the amount of the reactive shows the variation of the degree of the series capacitor compensation. So, K will be changing in each of the cycle. So, there is a fast acting devices is required to act on it. Of course, you change the thyristor triggering angle, and thus you can control the actually amount of the reactive power injected into the system, as well as the compensate the value of the impedance into the system. Either of it, you can have a converter based solution, you have also the impedance based solution. So, K is maximum when this one is actually more than and when it is 0, and it is 0 when actually it is negative. With the maximum K, the effective line impedance is minimum, and consequently the electric power transmitted over line is maximum. When K is 0, then effective impedance is maximum and the power line transmitted is minimum, and the power transmitted by the line is minimum. The illustration shows that K controlled in a bang bang manner. Bang bang manner means actually positive and negative, like your ACs. Okay, you set it actually at 25 degree centigrade or 26 degree centigrade. So, how it will be controlled? So, there will be a hysteresis band above which it will be on depending on the sensitivity, and below which it will be off. So, it may be on when actually temperature goes little above than 26 degree, maybe 26.2, and then it will not close at 26 degree, and it will bring the temperature maybe to 25.8, and then it will close. So, on and off in that manner It is called bang control. So, bang manner, output of the series compensator is varied between the maximum and the minimum values, and for this reason we require a hysteresis loop to operate it. So, what happened then? Indeed, this type of control is the most effective for damping large oscillation. So, now we have talked about the theories of the series compensation. Now, we are actually going to discuss different type of series compensator, and these are the first we will take the impedance based series compensator that will change the impedance of the line. Thereafter we will see that actually the converter based series converter where actually it inject the voltage. Both will be discussed. Let us first take the different type of impedance type series compensator, that is basically GTO controlled series capacitor. So, you have advantage of switching on and switching off since it is GTO based. So, you have a on off control. So, you can have a this is a full control device. So, you can use this GTO. Otherwise, you have a thyristor switch series compensator. You can only change the alpha to control the flow of the current through the capacitor. In that way, you actually control the impedance. So, action will be taken after 10 millisecond only in case of the hour system like 50 hertz. And excuse me, thyristor control series capacitor TCSC, that is also thyristor control. Let us see how does it work. So, you will place this capacitor in a transmission line. Let us recall our first diagram that we have a two model theory. Thereafter, we have put a capacitor, they have to split it the inductor XL by 2, thereafter again XL by 2, and this is our model. And here it will be a variable capacitor. So, an elementary GTO thyristor controlled series capacitor, that is in abbreviation we will see there is a lot of abbreviation, and so students are requested to familiar with those application, and it will be very much used and practiced also in industry. So, GCSC was proposed by Cardy in 1992. So, this solutions came around 25 years ago. So, it contains a fixed capacitor in parallel with the GTO or the equivalent switch that has the capability to turn on and turn off according to the command or the correct signal. The compensation scheme is interesting in that the perfect combination of well established TCR. So, we have discussed TCR. So, that is same as the TCR, thyristor control reactor, and having a unique capability of directly varying the capacitor voltage by delaying the control. Please recall our TCR. So, we will be having a thyristors in parallel. What happened? It is very simple. You do not turn on these switches, ultimately the total capacitor will be inserted into the transmission line, and gradually you can bypass it. You delay it by an angle alpha. So, you know till angle alpha you have a maximum capacitor, and after alpha you have shorted this capacitor. So, thus accordingly you can change it. So, it works on a little negative logic. The objective of the GCSC scheme is to control the AC voltage VCC across the capacitor at a given line current I. When GTO or the high rating IGBTs valve is closed, the voltage across the capacitor is 0, that is what I was telling, and when the valve is open it is maximum. For controlling the capacitor voltage, the closing and opening of the valve is carried out in each of the half cycle in synchronism with the supply frequency. So, you require a PLL also, phase lock loop. The GTO valve is stipulated to close automatically through the appropriate control action wherever the capacitor voltage crosses 0. In the thyristor valve, the TCR opens automatically whenever current goes 0. So, that is the way it will operate. So, let us see the waveform of it. So, this is the current and ultimately it leads the voltage by 90 degree. So, turn off of instantaneous instant of the valve of the each half cycle is controlled by the turn off delay angle gamma, where actually gamma is basically 0 is less than pi by 2 with respect to the peak of the current. So, you see that because it will be turned off by, it will be a delay angle will be 90 degree. When opening of the valve is delayed by an angle lambda or with respect to the crest of the line signal, then the capacitor voltage can be expressed with the definite formula. So, it is Vc will be basically 1 by c integration of lambda to omega t. So, I dt, so 1 by omega c. So, it will be omega t minus sin lambda. So, for the subsequent negative half cycle same will be followed. So, ultimately this is actually V lambda. So, this is the voltage and which you can control, and if you don't give any triggering, so this will be the case. So, you can have a control over it by this. Similarly, same thing happens in the negative half cycle. So, ultimately this is the current and ultimately this is the voltage uncompensated or when actually you do not trigger. So, total capacitor comes into the picture and this is the actually the Vc with lambda. For subsequent half cycle intervals, the sign of the terms become opposite. So, it is quite common and this is the application of the negative half cycle. So, what we can talk about the GCSC compared to the TCR we have discussed in the shunt compensation indicates that the equations are formally identical and can be interpreted in the same manner. So, automatically it turns out that the instant of the voltage 0 crossing, this process actually controls the non-conducting or the blocking interval of the angle of the GTO. So, the turn off delay angle lambda defines that the prevailing blocking angle, there is a conduction angle, that is pi minus lambda. As the turn off delay angle increases, the correspondingly the increasing the offset results in the reduction of the blocking angle of the valve and the consequent reduction of the capacitor voltage. So, capacitor voltage can be controlled in that way. So, what happened? This is a waveform for GCSC. So, you see this is a current and this is a VCC. So, this is actually it is not been triggered and thereafter you change this angle to lambda 1 and lambda 2, gradually current or gradually this voltage will reduce and this is a VCC and ultimately effectively you get change in VCC as required. So, this is evident that magnitude of the capacitor voltage can be varied continuously by the method of the turn off delay angle control with the maximum lambda equal to 0 to lambda equal to pi by 2 and where effective capacitor voltage V lambda is having a fundamental value of Vc lambda. So, what are the takeaway? So, this is the takeaway, the current of the thyristor control reactor is identical and derived from the voltage source GTO thyristors and control the series capacitor. It confirms the duality between GCSC and TCR. duality between GCSC and TCR. So, TCR is a switch in series with the reactor, and GCSC, since it employs the capacitor, it is dangerous to put capacitor in series. So, GCSC is a switch in the shunt with the capacitor. TCR is supplied from the voltage source and the transmission bus voltage. The GCSC is supplied from a current source, the transmission line current, and TCR valve is separated to close at current 0 and it operates at voltage 0. So, GCSC at voltage 0. So, thus we conclude the GCSC. We shall take other impedance based series compensation in our next class. Thank you for your attention. Thank you.